Hi everyone, and welcome to today's lesson on Algebra of Functions Applications. So today we're going to just look at several different applications of the types of functions we've been considering over the last week or so. We've looked at sum and difference of functions, product and quotient of functions. We've also done a composition of functions. So those types of scenarios are going to be worked into a few of the examples we're going to consider today. So first example involves a business situation involving profit, revenue, and cost. One important formula we need to be aware of just to start off with is how to calculate profit. It is the difference between revenue and cost. So right away we see, okay, a difference of functions working in here. Now, we have a graph that we're going to consider in this case that actually gives a function for revenue and a function for cost. Now, what we're going to be asked to do in this question is actually sketch what the graph representing profit would look like. One other thing we're going to be asked to do here from the graph is estimate the break-even point. Now, the break-even point, one thing we need to be aware of for break-even, if a company breaks even or if a business breaks even, what we know about that scenario is, well, the revenue and the costs are equal, so profit would be 0. So the graph we're going to consider gives revenue and cost. So we can see both of those in this case. Now, one thing that should hopefully jump out at you right away did want us to look for the break-even point. And we established that the break-even point would be where profit was equal to 0, and that would result from the revenue and the cost being equal. So that specific point actually turns out to be right here, right where the two lines cross. So if I estimate where that is, so it looks a little bit past 12. So if we wanted to say make a round estimate, maybe 12.5 would make sense. And then as far as the actual cost, well, my vertical scale here is going up in increments of 100 per grid square. So maybe we say that point is at $625, let's say. I'm just going to highlight the fact that this is the break-even point. So what we'll now do, we've kind of highlighted one specific point on the resulting function. So I'm going to be graphing this in green as it turns out, but we need to sort of have some other points to work with. So what we'll do, it would make sense to sort of look at both the revenue and cost functions and pick some points strategically where we can clearly see ideally nice vertical components for the values so we can subtract them fairly easily in this case. So what I'm going to do is I'm going to highlight some points on the revenue function that I think will work nicely to use to calculate differences. And then I'll do the same thing on the cost function. Now, one thing to kind of keep in mind here, so I've highlighted the points I'm going to use from the function in blue, and then similarly I'm going to use the ones from the one in red. Notice that I'm picking points where I can see specifically the cost function has a nice vertical component to work with as far as plotting it. It'll just make the difference a little easier to graph. One thing I should sort of be aware of here is both of the functions were given, so the revenue and the cost are linear functions. So if I add them or subtract them, the addition or subtraction of two linear functions is still a linear function. So I'm going to get another linear function here when I do the difference. Right? So what we'll do, we'll basically say, okay, I am doing revenue minus cost. So the function in blue minus the function in red. Now notice to the left of my break-even point, the cost function is actually above the revenue function, which means I would not be making a profit. I'd actually be losing money. So one issue we would have here is, well, I'm actually going to get a negative value for the vertical component here. If I do 200 minus, in this case, 500, I would have to picture being at negative 300 if 4,000 units were sold. So I'm going to kind of imagine where that would be. So I'm going to have to kind of predict, 3 grid squares below. So let's say, I'm just going to estimate, but I'm going to say somewhere around there. And that would again be at negative. I've got the break-even point already graphed. Now if I look here, so anywhere to the right of the break-even point, I see that the revenue exceeds the cost, so I should have a positive profit. So if I take for 17 as my horizontal component here, the difference in the vertical component, so 900 minus 700 would be 200. So I would have a point right here, 200. And then the difference starts to get a little bit greater as I go along. So 1200 minus 800, I would be at 400. So I'm going to have a point here. And then I need a little bit more room to see where I would be next. So picture if I'm all the way over at 38 for the number of units sold, I would be at the difference between this one here is 1900 minus 1000, so I would have to be at 900. What I would be able to do at this point is just connect those points with a straight line. Keep in mind the point at the bottom here I kind of had to estimate. Okay, so I will put an arrow on the right end of my profit function. And then similarly at the left end here, one thing I'd have to consider, I could put an arrow here. So you would actually stop. I would extend the graph to the point where I got where the number of units sold was 0, because you're not going to sell negative units of an item. The function in black here does represent the profit, and we again have highlighted the break-even point. Okay, example 2. So this one, we're not going to worry about graphing in this case. We actually have a function whose equation is given to us. And what it is telling us here, so we're looking at a small electronics company where we actually have a function representing the cost of manufacturing. Now one thing I'm going to highlight here is the fact that it says X thousand Bluetooth cell phones. Okay, so again, if I had my X value is 2, that actually does represent the cost for manufacturing 2,000 phones, not just 2 phones. Now the other piece of information we're given here is we actually are told the company is predicting that if they sell, and again this says X thousand phones, the price is going to be set at, so 350 minus X. Determine the function to represent the revenue for this company. Right? Now one thing we will do to start off with, we should sort of define a variable to represent revenue. And then what we do need to realize is how to calculate revenue. So revenue will actually be equal to, in general, the way we would calculate this is the number of units sold of an item times the unit price per item. Right? So we're going to have to adapt this to our specific situation here. So the number of units sold, if I just make it X, again, X without the 1,000 attached here would be an issue. So I'm actually going to have to multiply 1,000 by X if I want it to actually represent a per 1,000 phones, right? But the unit price I don't need to adjust. That was what we were told. It was just 350 minus that. As far as a function to represent revenue in this case, right? Now we're going to use that. So the reason we're asked for that in part A is because now we're actually asked to determine the function to represent profit for this company. Right? So similar to the last question, I'm going to do a let statement just to define a function to represent profit. So then we will have, and similar to the last question, P of X, so it's got to be the difference between the revenue and the cost. So we're going to do the difference of R of X minus C of X. So what we would now do is actually replace R of X with what we had determined that it was going to equal. So that was 1,000 X times 350 minus X. Then I have to subtract from that the function C of X. Now one thing I have to be aware of here, that function was a polynomial function that had 3 terms. Now if I'm subtracting that, it would be wise to actually picture C of X written within brackets. So I actually have, so picture 200,000 was the first term in that function, plus, and then the next part was the 10,000 X, and then plus the 125 X squared, right? So if I put everything in the brackets, I don't have to worry about messing up any of my signs here. I am going to drop the brackets here momentarily though, and then my signs will switch as a result. This is actually a quadratic function, and it's a quadratic function that would be opening downwards because of the negative lead coefficient here. Right, so the fact that it's a quadratic function that opens down, we would know that the vertex has to be the maximum point for the function, which would then entail that, well, this means the company's profit does have a maximum attainable value, which would make sense because, you know, there has to be a cap at some point on profit. Profit does not. So there is one last question to consider for this example, and it says, to actually figure out what the company's profit would be if 4,000 cell phones are made and sold. Now, the only thing that's potentially tricky about this question is how to interpret the 4,000 cell phones. Okay? And it would be, well, what do I set x equal to in my profit equation? So as far as what we would do from here, now it's just a matter of evaluating our profit function at an x value of 4. All right, last example for today, example 3. So we are told that the radius, which is in this case measured in centimeters, of a puddle is changing according to the formula. So it's a linear relationship. It is one that's decreasing, though, as far as the fact that we're taking away 2 times t here. Picture if you were to graph that, as the t value gets larger, the value of r is getting smaller. So t does represent elapsed time in this particular case. Now it says to find an expression for the area of the puddle in terms of time, and then use it to find the area of the puddle after 10 hours. Now, one thing that wasn't specifically specified here was how to calculate the area of the puddle. Now, one thing we can assume here is that it is actually a circular puddle, just based on the fact that it's talking about radius. So we do know that the radius of the circle is measured in centimeters, and we do know that we're working at time in terms of hours here. So we do know one other thing. This would make sense. The puddle would get smaller unless it was raining. If, let's say the weather gets nice and it's getting hot outside, the puddle will get smaller over time. Okay, so the one thing we would need to do right off the bat is, again, picture how am I going to come up with an expression for the area of the puddle. Regardless of whether it's in terms of time or not to start with, we do need to know how to find the area of the puddle. Because it's circular, we need to know the area of a circle. You may recall from previous grades, to calculate the area of a circle, the area of a circle is just pi times whatever the radius is squared. Right? But we want the area of the puddle to actually be in terms of time, as it said, right? One thing we need to realize is, well, we have an expression for radius in terms of time, so we can actually replace r with an expression in terms of time. So if we picture basically what we're doing here, the reason this relates to this unit is we're going to do a composition of functions. So we have area defined in terms of radius, but radius can be defined in terms of time. So if I basically replace radius with a function in terms of another variable, I've now represented the area as a composition of another function. So we will end up getting pi times, picture 50 minus 2t, all of that squared. That is equivalent to the relationship we need to work with, which is area, but now it's expressed in terms of time rather than just r. Right, so we have a composite function for area in this case. Now it wants us to figure out what the area is after 10 hours. So picture A equaling pi times 50 minus 2 times 10, all of that squared. So the inside, picture 50 minus, in this case, 20, so that's going to be 30. I'd have to square 30. So if I wanted to express the area exactly, That would be 900 times pi. So that would be an exact solution. Or if I wanted to approximate what that is, again, pi, there should be a pi button on your calculator. It's approximately equal to 3.14, but if you use the pi button on your calculator and multiply it by the 900, you're going to get approximately 2,827.4, and the units in this case would have to be square centimeters since this is area. Okay, so if you consider the examples we've talked about today, first one was a graphical question where we did a difference of functions. The next one involved, turns out, another difference of functions, but we actually had equations to work with. And then the last example we considered was just a composition of functions. In class, you're going to get a chance to work on some questions similar to this. But if you have any questions related to any of the examples I've covered today, just make sure you ask them in class tomorrow. Have a good day. See you. Bye.